So the first module that I have is not necessarily IoT, but it is more to do with data-driven analysis. So, so for each of the problems, I have a actually background genesis why I got into this problem. So the genesis is that I was in 2014-15. I was working on cognitive radio, not conventional cognitive radio physical layer, but I was interested in energy optimized cross-layer optimization actually. So we came up with some technique called if I am given one particular channel. So there are multiple variants of the work, but how we got into these things, if I am given one particular channel which which can be harnessed by intelligently figuring out whenever there are temporal voids. Okay, so basically a wireless channel, I am as a secondary user trying to use the channel, and then what I need to do is I went by classical approach that I need to smartly figure out when the channel is available and when this channel is not available. So so this I'll come back to these things and quickly go into the diagram and then come back to here. Yeah. So basically these are channel given. This is the temporal profile, and the channel is sometimes busy, sometimes red is busy, let's say, and green is available. So now I, as a secondary user who is not licensed to use the channel, I need to utilize these green portions smartly and avoid using the red portion smartly. But my problem is that I do not know, because I don't have any control over the primary user behavior. So I as a secondary user am coming into the channel and then try to estimate whether the channel is available. So I'm doing sensing, channel sensing, and if at the time of channel sensing, if I find the channel is available, meaning that is energy captured, energy detection method, let's say, energy detection method says that the channel is available, detected energy is below certain threshold, then I am assuming the channel is available. Now the next question is how long channel is available, how do I predict it? And that is one challenge, right? So I sense this channel is available, but how long channel is available I need to estimate properly so that I can utilize the rest of the time. And likewise, if the channel is unavailable, if it is I am coming and sensing the channel, and if channel is red, then I need to assess or estimate how long channel is going to be red. Otherwise, what I will do, I will continue to sense, that is wasteful. If I sense quite sparsely, then I might possibly, if I sense too far away, then I might miss up certain green portions. So I need to sense intelligently so that I don't waste energy unnecessarily in sensing. Okay, so that was our motivation. We call energy aware, energy efficient dynamic spectrum access. We named that. Now to do that problem, we made a basic assumption. Let's go back to our motivation actually. Now that's how I will connect these two actually. So going back over here, so this is cognitive radio is what we were interested in, and I am talking about temporal on-off void channel void utilization. Okay, so there are primary users and I am the secondary user, let's say. Okay, who is trying to utilize the channel without affecting the primary user actually. Okay, so in fact at that time, 2015 actually we conceived these studies, 2014, 13, 14, but this current presentation is about, so LTU is actually one standard. This LTE standard, they were actually evolving these LTU unlicensed, and they were targeting to utilize this Wi-Fi band without affecting the Wi-Fi users actually. Okay. So right. So this is what I was talking about. That I am interested in these characterizing these on-off periods, on-off void and unavailable periods. So what we did for having a tractable analysis is that we modeled these on duration and off duration as exponentially distributed with different parameters, meaning that this is on duration is exponentially distributed with parameter, let's say lambda, and and off duration means channel is busy, and on duration means channel is, it could pose other way. For me, let's say off duration is green and on duration is red. Go back again to this. Yeah. So on duration is red and green is off duration. Off means channel is available. So we model these as exponential distributed and these are exponentially distributed. This if you think carefully, then this off duration means that a channel is unavailable, and on duration means, let's say, beginning of an on duration means a call has arrived. Okay, beginning of an on duration meaning that a call has arrived. This is beginning of an on duration. This is beginning of an on duration. So beginning of on duration is call arrival process. So I could have made a simplifying assumption that the beginning of call arrivals is, if you look at again classical assumptions, we could have assumed Poisson distributed call arrival process, okay, or packet arrival process. Packet arrival process would be modeled as just Poisson distributed. But the problem is that if I consider arrival process as Poisson distributed and packet size as exponentially distributed, then this is rather cruder approximation. Instead, this on duration as exponentially distributed and off duration as exponentially distributed is a little bit better assumption. What I mean is that this sum of on duration and off duration is not necessarily going to give you Poisson distributed arrival process. This models the arrival process better actually. Okay, that was our motivation, that we are doing a little bit better than Poisson distribution. But what we went with this assumption because we could still manage to do a tractable analysis. So we did this analysis. We actually published this paper in Transactional Mobile Computing. But while we published this, we were actually questioning ourselves that how good is this assumption? Can we actually figure out how this should be, this should look like? We actually tried to characterize some data, characterize this. Again, go back to this. So what we did is that we have considered this. Going back here. So we considered exponentially distributed this on duration and off duration, and at that time we figured out a lot of literature. So they were considering that okay, this is on-off distribution is one, but there are other assumptions people have made called Pareto, generalized Pareto, hyper exponential, all sorts of so-called tractable distributions people have considered and people have published in different transactions. So, and we correspondingly went by our approach and we published something. Of course, the other assumptions could be made for different other contexts, not necessarily cognitive radio, but this channel availability was used to be characterized by this actually. And we were questioning while we were finishing this work, and we then thought of let us characterize this. So what we did is we actually considered this Wi-Fi channel to figure out what is the packet arrival process. Okay, we created a control environment that nearby all Wi-Fi access points were turned off, and this is the experiment that we are talking about here actually. So we consider this, and we have a generalized environment. I will come to that. So there is a access point, and everything else is closed. And through this access point, we created a Skype call or some transmission process. Let's say FTP. So control environment we call. And this Wi-Fi access point is collecting data or basically extending the data from this source, and this is going to the internet, going to the other end actually, other receiver end, wherever it is. And then we used WASA to capture this packet traffic, and using these one software defined radio, and then we analyze this traffic distribution. We analyze the traffic actually. And so further details that how we measured, we had some EV certificate we used for that purpose. And what we have here is by capturing this energy detection method, first thing that we notice is that we have some kind of PT distribution actually here. So this there is some about this energy level about -70 and energy level somewhere varying somewhere here actually. So we figured out that possibly this could be the noise floor, and this is the portion of interest. Likewise, this is the floor, and other interesting thing here is that, so this is the control environment and this is the generalized environment. Generalized environment, we have a place in our institute where there is a kind of a coffee shop and a lot of students, faculty and outsiders, etc. sit down, have coffee, etc. So basically, we captured whatever is being exchanged, not necessarily Skype traffic or FTP traffic. We use this SDR, and we figured out that we have this similar noise floor, but there are some other peaky distributed scenarios also. So this is the number of received samples actually. So this is this one. From this number of received samples, what we wanted, we figured out the probability distribution function of the busy period and idle period. This is for the generalized environment, and for the idle period we have this kind of similar distribution which I have not shown here. Now we see that this probability distribution function of idle period is showing a peaky nature, that this is having, let's say, about 0.002 millisecond is the probability of having 0.02 millisecond as busy period is highest. Next probability is about 0.3 millisecond and then 0.6 millisecond and so on actually. And likewise, idle period distribution is also showing to be quite peak here, and then there are looks like a sum of the something. So two things caught our eyes actually. That remember that we were modeling this and this as exponential distributions. Okay. In our transaction mobile computing paper, we modeled these distribution as exponentially distributed, these as exponentially distributed. Now, how does they match? How do they match? They are far away, right? So this model cannot be at all close to exponential distribution. Okay. This is very peaky. This is also peaky and looks like some peaks, but these both are far away from exponential distribution, and also they are quite far away from any other distribution that people have considered. So that was actually a very interesting observation. Now the question is that what to do with this? What to do with these distributions? So we need to characterize that, as I mentioned. If I can characterize this distribution, because this is no empirical, this is more believable actually. And more interesting thing is that because this is empirical, I can actually have my SDR, and then SDR can possibly collect some traffic in the daytime, and it can figure out corresponding distribution. In the night time, when the people have gone away from the coffee shop, maybe they will figure out another distribution and so on. So it can continue to empirically capture the data and then generate the corresponding distribution. And then using that distribution, I could go back to that utilize these on-off distribution based approach that we are talking about. Okay, so now this is my empirical distribution, these two are empirical distribution. Now next task is that how do I model these distributions to have a tractable mathematical form. Okay, and those who are familiar with, okay, all of us are familiar with probability mass function. Okay, so this is somewhat close to probability mass function, but not necessarily very close. The probability mass function is that there are some spikes, right? The sum of these, what is that called, delta functions, okay, at particular location. But these are not necessarily delta function. These can be rather better approximated as individual Gaussian. One Gaussian peaking at some point, another Gaussian peaking at some point, another Gaussian peaking at some point, and so on. Here one Gaussian, and possibly there are other Gaussians and peaking at nearby points actually. So these can be modeled as Gaussian mixture model. So we call GMM. Actually, this is actually a well-known theory. We have not developed the theory. The theory existed. Now we went to one-dimensional GMM, utilize the one-dimensional GMM to characterize these two distributions. Okay, that is the next task actually, and that is actually a known theory in the literature. So these, how do I characterize? So this is by inspection we figured out that GMM is the right model to go for actually. Okay, now what is GMM? Gaussian mixture model is actually sum of Gaussians, as you can see. This is the PDF of a distribution, random variable X, and this is a sum of Gaussian with different weights. Okay, Wj is the J Gaussian weight, and then each Gaussian has its own mean and variance, and then you the number of peaks. In this case, I am visibly, let's say, seeing that there are 4 peaks or 3 peaks, etc. But we can actually model, if I don't have any idea even, I can model this. So j equal to 1 to k, k could be actually infinity, okay, and so on. So now this is what this Gaussian mixture distribution is actually. So if I can figure out 4 variables actually, k, wj, mu j, and sigma j, then I can characterize the distribution, empirical distribution, into a Gaussian mixture distribution. Okay, and now the next task is that how do I find k? How do I find these four variables actually? So this is the simple technique, known technique rather, expectation maximization and k-means clustering. So k-means clustering, that this is k actually. Is normally in the image processing, this Gaussian mixture is used in 2-dimensional Gaussian mixture. So k-means clustering coming from there. But in our case, k is 1-dimensional actually. In this case. So k is the number of clustered components, and this is the sum of clusters. And we start with k equal to 1, and then see what is the empirical distribution we can find. And then what we do is we try to feed this with k equal to 1. We try to feed this model distribution with the geometric, with the empirical distribution, and then figure out the closeness of fit of these two distributions. Because my empirical distribution is known, to me, and by considering k equal to 1, I try to find out one peak and then figure out what is the height, and then I'll come to the distance measure, etc. And then if I find that this distance between this empirical distribution and the model distribution is far, then I increase the value of k equal to 2, k equal to 3, and so on, and I keep on doing, because I have control. I can go up to k equal to infinity. Okay? So, and as we will see, if I go for k, larger value of k, my competition and complexity also grows, right? So I would like to rather stop as fast as possible, as small value of k as possible, and then there I correspondingly find these values. So this is the iterative process actually. So k-means clustering and expectation maximization. We did some modification to convert this algorithm fast. Basically, from the inspection, we figured out that we don't necessarily need to start with k equal to 1. We started with k equal to 3, and that helps us something. So now I was talking about this distance measure actually. So dk is the distance of the modeled Gaussian mixture model, and distance of this model distribution with the empirical distribution. And what is the distance? Actually, there are a lot of distance measures available in the literature, information theoretic distance measures available. So this is the gx and fxk. So fxk is my model distribution for a chosen k, and the gx is the empirical distribution actually. So this is the CDF. Okay. So CDF of the empirical distribution and the model distribution. So this distance measure is given, known as called Kolmogorov's mean of distance. There are other distance measures we chose at that time. We had no idea, just picked up one distribution, and what we wanted is that we figured out, we defined for ourselves that we want to restrict this dk to, let's say, 0.5 or some value actually, and then we continue to increase. So now, by increasing this value of k and then figuring out this expectation maximization algorithm, running this expectation maximization algorithm to find the wj, mu j, and sigma j, we see that this is my empirical distribution, this black line, and this is 3gm, 4gm, 5gm, and these are other distributions that other people have considered. These hyper exponential is our approach, and so on. we only consider, and generalized Pareto some other researchers consider. So as you can see here, this empirical distribution is the black line, continuous line. Compared to that, other distributions are doing quite poorly actually. So hyper-exponential is here, generalized Pareto is here, they are quite far off actually. On the other hand, as I grow from 3GM to 4GM to 5GM, 5GM is not very well visible. In this diagram it is better visible actually. 5GM is almost overlapping with this. And interestingly, it will match. If not 5GM, maybe at 6GM, or if not that, maybe at 10GM it will match actually. What that means is that this Gaussian mixture model is actually very powerful, that I can choose the least value of k and match the model distribution with the empirical distribution to as close as possible. Okay, as close as possible, as close error margin that is given to me. Okay? Error margin is given to me, the dk that I was talking about. For a given dk, I can model any empirical distribution to come up with a model. Okay, so and this is so powerful that in fact exponential distribution, which is continuous distribution actually. Continuous distribution also can be modeled as a Gaussian mixture, but we normally do not use this Gaussian mixture model for modeling known or continuous distribution, because number of components required will be infinitely large and computational complexity will be growing exponentially. We want to minimize it. Okay, so in our case, our first task was to model this empirical distribution to what is that called, Gaussian mixture, and in our case we figure out that beyond 4GM or maybe at 5GM it is saturating. We wanted to stop there actually, because going for higher k is going to be wasteful in terms of computational complexity here. So some of the results actually exponential. So we distance measure for controlled traffic environment, VoIP site and FTP. These are the two control environment, and these are general environment actually. So exponential distribution distance measure is 0.56 and generalized Pareto this, and as you can see 1GM 0.49, 2GM reducing, and then beyond 4GM it is kind of saturating. Okay, so and it might be reducing a little bit, but I figure out that it is like a trade-off, right? How much of computational complexity I would like to afford versus how much accuracy I am getting for. And likewise, for the IoT period also, it is kind of saturating at 5GM. Okay, it is not reducing further. So we kind of concluded that 5GM is sufficiently closely modeling these empirical distributions. Likewise for FTP, likewise for general environment. So that is one part. And the next part is that now using this developed model, we want to do this, go back to our proposed algorithm, that this cognitive radio, and instead of on-off distribution with exponential and exponential, these still on-off, but on-off distributions are not necessarily exponential distribution or other hyper-exponential, etc. Instead, they are these two distributions that we model actually. Okay, so this is my, so the way it works is that this is my PU activity, primary users channel usage activity, which I don't have control in, and SU secondary radio is trying to utilize the channel in this way actually. So these are the SU is sensing, and then if SU senses channel is idle, then SU will try to grab the channel, and it will. In this case, it is going to be, let's say, conservatively predict that it will transfer only 3 slots, and then it figures out that again it senses, and again channel is available. Now what is happening is that it is going to collide with this busy period, and that is what is unwanted. Okay? So for m equal to 2 and so on. So this is so now instead of using that distribution that we considered, we go by our empirically observed and model distribution. And now quickly I will run through these some of the results here. That our previous one where we considered exponential distribution versus proposed GM are giving twofold benefit. One is that my channel utilization, which is measured as throughput, is improved. So these white box bars are the proposed distribution, and blue boxes are blue bars are the previous approach. It is improving, and also energy efficiency is improved because intuitively, because I am more intelligently able to figure out how long I need to keep myself idle. So when I am not sensing, I am putting myself in sleep period or deep sleep period. Okay, overall is improving. And likewise, there is another paper around that time. This was the paper we originally compared with for our PhD, and they considered this, they call residual time distribution based scheme, RIBS actually. They basically kind of model this residual idle time, and residual idle time distribution was modeled considering hyper exponential hyper exponential. So they considered hyper exponential as a deep distribution. Okay. So with that, they considered this thing, and we compared that with our approach. Again, here hyper exponential is that PhD 14 paper. Exponential distribution is here. Hyper exponential is this one, yellow, and then white box are the other ones. Okay, so basically this is doing better compared to any existing approaches that we have. Okay, so this is a kind of a motivation for us that this data-driven technique is doing better compared to other tractable models that are being used so far in the literature. Okay, and this model is actually much powerful compared to the other distributions considered, because those distributions, hyper exponential, generalized, Pareto, etc., these distributions are again considered to be known. That means that process is considered to be stationary. So, for example, if I am trying to utilize this, let's say Wi-Fi channel's availability in the daytime versus evening time in a campus area or anywhere changes with time actually. So these considered models are not capturing the dynamics of the environment actually. Whereas in our empirical approach, so to take away here, so theoretical models for channel occupancy characterization are quite inaccurate, as we discussed. Given the channel can be characterized using data-driven technique, which is what we consider empirical and modeling. Data-driven approach offers significantly better channel utilization and energy efficiency. Also, some results are shown. Now, there are some challenges actually. So this study that we have done, we have modeled, we have captured empirically the channel availability and unavailability. We modeled empirically, and then theoretically we say that if I can capture these voids are on the order of milliseconds, so 0.1 millisecond, 0.05 millisecond, etc. And if I can capture these voids so quickly, then I will be able to utilize these voids the way I mentioned. But the challenge that we figured out is that after capturing the data, if I want to utilize these void periods on real life, then I need to process this data so fast on the order of fraction of millisecond, so that I can use these voids which are on the order of fraction of millisecond. But what we are figuring out is that by processing the data in our current technique using MATLAB based processing, it was taking somewhere tens of seconds actually. So what that means is, the inherent advantage of data-driven approach is in adaptiveness. This is actually benefit I mentioned. Temporal voids are on the order of millisecond. Now the problem is the order of computation time for channel occupancy characterization is on the order of several seconds. So what that means is that the way we have been processing the data using software-defined radio is not sufficient to truly utilize the resource. Okay, so what is required here? We have some thoughts, but we did not proceed further. We could not actually. So we feel that if these channel empirical data that we are capturing, if the processing can be done possibly much faster using maybe higher end processor, or maybe at the FPGA level, then the interface related this delay can be minimized, and that possibly can handle that thing. So significantly efficient real-time computation resources are required to effectively utilize the temporal coherence. Okay, so this is actually a task to be done actually, to how to actually utilize these resources efficiently. Particularly, so this question is actually not so bad in the sense that if the system is dynamic, if the dynamics of the environment is fast enough, then only this is major problem. See, what I am talking about is that if I observe, let's say from morning 10 to 12, the channel availability environment does not change significantly. Statistics does not change significantly. So what that means is that in the model, I model the empirically capture the data in morning at 10, and then possibly next 2 hours I can utilize that to reasonably work well. But if I want to use that throughout the day, it will not work well, because maybe 12 to 2, the behavior of the channel occupancy changes, and as a result I need to retrain actually. So that the dynamism has to be considered. So this is if the environment changes very fast, then this is not sufficient. Otherwise, this can be still made use of. There is some room to improve it.